Hello. In this presentation, I discuss the characteristics of the normal distribution and strategies for assessing normality or lack thereof using SPSS. Copies of this PowerPoint and the data are provided at the links underneath the video description, so be sure to download them and follow along. So what are the characteristics of the normal distribution? The normal distribution first is a family of distributions, and although each distribution in the family varies depending on its mean and standard deviation, all normal distributions have certain fixed characteristics. Each distribution is symmetric, with the mean, median, and mode of the distribution falling at the centermost point in the distribution. So when a distribution is symmetric, you'll notice that 50% of the distribution will fall at or below the centermost point in the distribution. The remaining 50% obviously is falling above. B, the distribution is bell-shaped. C, there is a fixed relationship between the area underneath a normal curve and the standard deviation of that distribution. And then D, the curve is asymptotic, meaning that the tails never touch the x-axis. The tails of the curve, which reflect extreme scores, come closer and closer to the x-axis without ever touching it. Any normal distribution can be described in the following way. X refers to the raw score, refers to the variable with raw scores on it, and basically this is read as scores on X are normally distributed, that's what the N is for, with a population mean mu and a population variance, which is the sigma squared that you see. One special type of normal distribution is the unit normal distribution. And the unit normal distribution can be described in the following way. Basically, scores on X are normally distributed but have a mean of 0 and a standard and a variance of 1, and that also means that the standard deviation is 1. Alternately, you might hear people refer to the unit normal distribution as the standard unit normal distribution or even the Z distribution. So here we have a figure where we have the unit normal distribution that depicts the relationships between standard scores, which reflect the number of standard deviation units a given score falls above or below the mean of 0, and the area underneath the curve. We see that the percentage of the normal curve falling between -1 and +1 standard score units, or z-scores, around the mean is roughly 68%. The percentage of a distribution falling between z at -1 and the mean is roughly 34%. The same percentage falls between the mean and z equals +1. So basically what we're referring to in this context is this area here. So you can see that between the mean of 0 and a z-score equals -1, that covers roughly 34% of the distribution. And between 0 and +1, that covers another roughly 34%. So if you sum those two areas together, that means that the area falling between -1 and +1 z-scores, or standard score units, is roughly 68%. Now in this illustration, we can see the percentage of the normal curve that falls at or below a standard score, or z-score, that's equal to +1. So that's this point within the unit normal distribution. And so you can see that basically if we sum up all of the areas up to this point within this distribution, it sums up to roughly 84%. And basically what this entails is that we know that with this area right here, this encompasses 50% of the unit normal distribution. If we add an additional 34% right here, that's what gets us the entire 84%. If we were looking at z equals +2, basically 2 standard score units above the mean, then in this particular case we can see that it covers 98% of the distribution. So that's basically reflected in this area right here, starting at z equals 2. That also would mean then that roughly 2% of the distribution falls above a z-score that's equal to 2. Now because the normal distribution is symmetric, we can also argue from symmetry that if we are at z equals -1, that means that 84% of the distribution would fall at or above that point within the normal curve. and then also at z equals -2, that would mean that 98% of the distribution would fall at or above that particular point. That also means then that 2% of the distribution would fall at or below a z value or a standard score that's -2, whereas 16% of the distribution would fall at or below z equals -1. You can see in this particular presentation or demonstration that again, that approximately 2% of the normal curve falls above a standard score that's equal to 2, and that would also mean that approximately 2% would fall at or below a standard score that's equal to -2. And if you sum these two areas together, that would actually sum up to 4% of the normal curve. If we want to find the area that falls between 2 points within the normal curve, we can also do that. For instance, let's say we want to find the area between a standard score of 1 and a standard score of 2. Okay, so in this particular case, at z equals 1, you can see that 84%, or roughly 84% of the distribution falls at or below that point. We know that roughly 98% of the distribution falls at or below a z value that's equal to 2. So if we take 98% and subtract 84%, that yields roughly 14%. So in this table, you can see right here it's 13.59% to be a little bit more precise. Now, how can we assess a distribution to determine if it is normal or not normal? So normality of a distribution can be assessed by A, examining the distribution for evidence of skew, B, examining the distribution for evidence of kurtosis, and C, that's an and or, performing omnibus tests for normality. So let's start off with the concept of skewness. Skewness refers to the degree to which a distribution is asymmetric. Skew can be assessed through visual inspection of histograms and box plots and through outlier detection. Moreover, one can consult skewness statistics and or test them for statistical significance. So you can see in the presentation down below, you can see that our figures, we have first off, we have a negatively skewed distribution, which is this one right here, and you can see the skew is reflected in this part of the distribution. Then we have a positively skewed distribution where the skew is reflected in the upper tail of this distribution. So with negatively skewed distribution, you can see that the lower tail is longer, whereas a positively skewed distribution, the upper tail is longer. Now, kurtosis is a highly misunderstood dimension of normality and is often misdescribed on websites and in published textbooks. And the most common misconception or mischaracterization of kurtosis is that it is all about the peakedness of a distribution. And in 1997, DiCarlo argued that kurtosis actually should be considered as reflecting the peakedness, the tailness, and the shoulders of a distribution. So it's not peakedness only. So in his presentation, he compared distributions with varying forms of kurtosis against a normal distribution. He described leptokurtic distributions, basically indicated by positive kurtosis values when centered at 0, as being peaked while also having thick tails. He also described platykurtic distributions, which are indicated by negative kurtosis values, as being flatter and having thin tails. So if you notice in the depiction from his article, you'll notice the dotted line in the box on the left represents a normal curve. The same goes for the box on the right, but you'll notice that the box on the left has a peak right here, but then also the tails are thicker in relation to the normal curve. Whereas with respect to the platykurtic distribution, you can see that it's more flat with thinner curves. You may also see in some textbooks a presentation that looks more like this that's coming from Rex Klein's book. And in this case, you'll notice that you have the normal curve, which is the non-dotted line or the full line, and then you've got positive or leptokurtic distribution and negative or platykurtic distribution reflected in the various dashed lines. Now, before moving on, I do want to mention that Westfall in 2014 has provided a mathematical and simulation-based argument that distributional peakedness is really not a defining characteristic of kurtosis. So he's arguing against DiCarlo's account and a lot of other accounts in the literature. So he argued that kurtosis is really about the extremity of scores in a distribution, and that matters most to kurtosis, as those scores that are falling between -1 and +1 standard deviations about the mean, which is where the peaks would generally be observed, generally have a very small impact on the computed kurtosis. So basically he's arguing that peakedness of a distribution should not be treated as relevant when defining kurtosis. So the reason why I'm adding this in here is just to let you know that there is a certain lack of consensus about what kurtosis really is within the literature. So now let's move on to our demonstration. So we are going to assess the normality of a variable using the Explore option in SPSS. So basically I have data from 80 individuals, basically fictional individuals, with scores on a measure of achievement and a measure of interest. And so the way that we can use the Explore option is to go through the menu for Analyze, Descriptive Statistics, and then down to Explore. And so when you click on Explore, then this box opens up, and you can move your variables over to the dependent list right here. When the plots, you can click on the plots tab right here, and when this opens up, you can ask for things like the stem and leaf plot and histogram, and then also normality plots with tests. So let me just briefly walk you through this in real time using SPSS. So this is the data in SPSS. We have our achievement variable and our interest variable. So we're going to start off with achievement because that's the first demonstration in the PowerPoint. So what we'll do is we'll click on Analyze, go to Descriptive Statistics, then go down to Explore. So when this box opens up, we'll move the Achieve variable over to the dependent list. Under Plots, we'll click on Histogram and then normality plots with tests. So next we'll click on Continue. If we wanted to look for potential extreme scores, the way we can do this is if we click under Statistics, you can click on Outliers, and that will give you a box with extreme scores. And I'm not going to show you that right now, but we'll click on Continue and then on OK, and now we get our output. So this is it right here. So you can see we have a box containing various descriptive statistics, tests of normality, a histogram, we have a QQ plot down here, and then we have a box plot at the very end. So let's go ahead and walk through some of the pieces. So first off, under the descriptives, you can see that we get a variety of pieces of information. We get the mean right here. That's for the achieve variable, that's 49.7696. You can see that we get the median for that variable. We get the variance and the standard deviation that's given right here. You can also see that we get the range that's given right here. But for the purposes of kind of demonstrating skewness and kurtosis, or looking at normality, we're going to pay most attention to the skewness and kurtosis statistics right here. So one simple rule is that a skewness value, an absolute value that's greater than 2, is suggestive of more considerable departure from normality. And so you can see right here that this value is negative 0.013. So that's clearly not meeting the threshold for what might be considered more substantial amounts of skew in the data. So at least descriptively along that dimension, there's evidence for normality. Similarly, we can apply that rule when it comes to evaluating kurtosis. So you can see right here we have a negative kurtosis, it's negative 0.429, and so again we're not meeting the threshold for a kurtosis value that might be considered more substantial or more extreme. Now some authors have suggested that you can basically carry out what amounts to be a z-test in order to evaluate whether or not the skewness and kurtosis values depart significantly from what you would expect with a normal distribution. So basically the z-test for skew just involves taking a ratio of the skewness statistic to its standard error right here. And so in this case, if we take that ratio, then we get a negative 0.048. And then the same process would be at play if we're looking at kurtosis. So just basically taking the kurtosis value of negative 0.429, dividing it by the standard error of 0.532, and you get a negative 0.806. And so basically the rule of thumb would be that if the z value is greater than 2 in absolute value, at least for the skew or kurtosis, then in that case you would have evidence of departure from normality. In both of these cases, the z values are clearly do not have an absolute value that's greater than 2. So both of those are consistent with normality. Okay, so these tests of normality, these can be considered omnibus tests of normality. So they're not looking at skewness or kurtosis individually, but sort of as a set. And so basically, both of these are, the null hypothesis is that your data are following a normal distribution. So the easiest way to look at this is just to look at the p-value that's printed out right here and right here. So the Shapiro-Wilk test is oftentimes kind of preferable when you're working with a smaller data set because it tends to be a lot more powerful than the Kolmogorov-Smirnov test. But you can look at both of these to sort of make a decision about whether or not you have evidence of a normal distribution. And so the basic idea is that if the p-value that's printed out is less than 0.05, then that would be taken as an indicator that the distribution departs significantly from normality. And if p is greater than 0.05, which is reflected again in the significance columns, then that would be evidence that the distribution is consistent with normality. So both of these tests are suggesting that our data are consistent with normality. Let me also note, though, that there are occasions where these two tests, the p-values, can be different enough where it would suggest that the tests disagree with each other. So just kind of keep in mind that can occur. It's also recommended, though, that in addition to these types of tests, you might also consider visual inspection of your data. So in other words, it's worthwhile to take more of a holistic view of your data when it comes to evaluating for the presence of normality. So here we have the QQ plot, which provides a plot of the observed values on the variable against those expected under the assumption of normality. And as the data departs increasingly from the regression line, this would be an indicator that our data is departing more substantially from normality. In this particular demonstration right here, you can see that the data lines up pretty closely with that line. Here you can see that we have a histogram that was printed out, and again you can just sort of look at this this depiction of the data in order to compare your data against what you would expect if it were normal. Here we have a box plot which can be further used to evaluate normality. The horizontal edges of the box in this depiction represent the 25th and 75th percentiles in the distribution. The line falling between the 25th and 75th percentiles is the median. And so normality would be evidenced by the fact that the whiskers appear to fall equidistant from the median of the distribution and basically extend the same length from the 25th to the 75th percentiles out. If you have one whisker that's longer than the other, then that would be some evidence of asymmetry with respect to your distribution. Okay, so now let's see what would happen if we examine the interest variable. So again, if we go through Analyze, Descriptive Statistics, Explore, put interest in the dependent list, looking at our descriptive statistics, now you can see that the skewness value and the kurtosis values, both of those are well above 2, suggesting a more substantial departures from normality with respect to this variable. And if we carry out the z-test, you can see that we get a z-value that's, for skewness, that's equal to 10.955. For kurtosis, it's 35.056. So both of these, again, are suggesting more significant departures from normality. When we look at our Kolmogorov, Smirnov, and Shapiro-Wilk tests, both of these are statistically significant, again indicating more substantial departure from normality. In our QQ plot, as you can see right here, most of the data points line up pretty nicely on this line, but we do have one case that just seems to be departing substantially, and this is actually evidence of a potential outlier in the data. If you want to identify what case that is, what you can do is in your output file, you can double click on the plot, and then basically if you'll go under the Elements tab and go to Data Label Mode, you can click on this and move your cursor over to that case, and you can see we have a number 1, which is basically indicating that person number 1 or case number 1 in the data set appears to be our outlier on this particular variable. Okay, looking at our histogram, you can see there's no great surprise. We have evidence of an outlier in our distribution. And basically just an outlier is an extreme case within the distribution, and outliers can be produced by a variety of things. One may be a data entry error, or some other type of error that basically creates an observation that departs substantially from the remaining observations in the distribution. Another possibility too, though, is that maybe that case is not really coming from the same population as all the remaining cases in the data set. Maybe it's actually coming from a different population. So just by looking at it visually, you're not really going to know which of those cases it is. So when you do have outliers, it's worth your while to go and inspect your data to look to see if there's any kind of errors that might have been producing that extreme observation. So in this box plot right here, you can see that the whisker, this whisker is a little bit longer than this other whisker, and you can see there's a case that's given. Actually, let me just kind of backtrack a second. This is more of an extreme case on the lower end, but case number 1, this is our outlier, which is on the upper end right here. So if it had been the case where we had more scores that are falling on this upper end right here, then this whisker right here would have been a little bit longer. Okay, so one other option for identifying potential outliers would be to convert the raw scores on your variable into z-scores, and then select those cases with z-scores that meet a particular threshold representing an extreme value. So a common threshold for identification of a case as being a univariate outlier is a z-score that's greater than 3. So in this depiction right here, you'll notice that I'm going through the Analyze Descriptive Statistic menu and then clicking on Descriptives right here. When this box opens up, I just move my variable over to the Variables box and then click on Save Standardized Values as Variables. And so when I do that, what ends up happening is that a new variable is created in SPSS that are z-scores. So it's just basically a conversion of the raw score on our original variable into a z-score. And the z-score basically, the z-scores have a mean of 0 and a standard deviation of 1 within the distribution. So you can see within this, our data set right here, the z-value for the first observation or the first case in our data set is 6.25727. That value certainly exceeds our threshold of 3, which suggests that we have an outlier in our data, and that is case number 1, which we've actually already seen in our previous graphs. Now, one limitation of going into your raw data and looking at the variable is that sometimes you can have a lot of cases in your data set. So then you're just kind of scrolling all the way down the data set to try to identify potential outliers. And so it can be really kind of a headache. So a quicker way of identifying potential outliers once you've created the z-score variable is to use the Explore option again. And in this case, we would go to Descriptives, Explore. We would move the z-score variable over to the dependent list. And when we click on the statistics box, we'll click on Outliers right here. And when we do that and click on Continue and on OK, you'll see that we get now a box containing extreme values. And you can see z-scores. It's got the 5 highest z-scores and the 5 lowest z-scores. And you can see case number 1 right here has that z-value that's equal to 6.25727. So this is really a quicker and easier way of sort of screening your data for outliers than just simply creating the z-scores and then scrolling down the original data set on that z-score variable. So let me just kind of briefly show you these steps. So here we're back to our original data set. And the first thing that we'll do is we're going to click on Analyze, go to Descriptive Statistics, and then go down to, we'll go down to Descriptives here. We'll move our interest variable over to the Variables box, click on Save Standardized Values as Variables, then click on OK. And so now we see that our z-score variable is included in our data set. And so you can see this is our case number 1 that is our potential outlier. So, but again, we can see that we have z-scores for all cases, and right now we only have 80 cases, but imagine that we had 500 cases and you were trying to identify potential outliers. It could be a real headache. So a quicker and more efficient way then would be to go through Analyze Descriptive Statistics, click on Explore, and basically we'll move this variable over and put our z-score variable in the dependent list. We'll click on Statistics, Outliers, and then Continue, and then OK. And so now we get our table that contains the extreme values. Again, you can see right here we have case number 1 where we have a z-score that's equal to 6.25727. And you can see down here that all of the z-scores in the upper end, with the exception of that case number 1, all of those do not meet the threshold as being a potential outlier. And then on the lower end too, we have negative z-score values with none of them meeting the threshold of 3 in absolute value. Finally, let me just kind of note one more graphical procedure that's similar to the QQ plot, which is the PP plot basically. And so basically to obtain a PP plot for our variables to evaluate normality, what we would do is just go into Analyze Descriptive Statistics. You'll notice that we can go down to PP plots right here, click on that. You'll notice that the test distribution is set at normal right here, and we're just going to move both of these variables over to this box right here just in the interest of expediency. So we'll move this over here, we'll move this one over here, we'll click on OK, and so now you can see we have a normal PP plot, basically probability by probability plot for the achievement variable, and you can see the data is lining up pretty closely to our regression line. And then for interest, you can see in this case right here that we have more substantial departure from the regression line in this particular case. So you can see that basically there's greater evidence of normality with respect to our achievement variable than our interest variable. So that pretty well concludes our demonstration. The last couple of pages in the PowerPoint are references, so be sure to check them out. Thank you very much for watching.